Yesterday, you were introduced to a lag compensator, and we have done one example. This example is actually taken from the textbook. So in here, we design a lag compensator to achieve 10 times improvement in the steady state error. Then we calculate, I hope you have looked into it, and we stop. This is the lag compensator that we designed. The 2 points which are important is 0.062 and 0.98. And finally, we get this. We stopped here yesterday. G controller or lag controller is 0.063 S plus 0.98 over S plus 0.062. And this is actually similar to the pattern of the transfer function of the lag compensator. S over 1 plus T, 1 over T over S plus 1 over alpha T. Right, so I just want to show again. This is taken from the book. Initially, this is what we want, 110. So that our S margin is about 70 degrees. Then we look into the gain, the magnitude. We get 24 dB. Then we design a lag compensator by giving minus 24. So we design here on the high frequency gain minus 24 dB. And until here, which is 0.98, 1 decade after this is 1 decade. Then we draw a line 20 dB per decade until we get another point. Here is 0.062. Then that is known as the lag compensator. Okay, so finally, this is the one that I showed to you. This is the transfer function that we obtain, and we can multiply all these with the original system, because we have GC, we have G. They are in cascade. So we can finally multiply. So this is the one that we obtain when we multiply all with this and with the original system. Okay, and I use MATLAB to plot to show you the difference between the uncompensated. Uncompensated meaning without controller, not yet controlled. Compensated means with a controller. In this case, we use lag. We can see that at the point that we interest, here is 0.98. We design at 0.98 radian per second. We can see that the magnitude is 0. This is what we design. And here we assume we get the scale is not that accurate. So I think this is 110, and the phase margin here is 70 degrees. We design and we obtain this. And we also make sure the red one here has the same magnitude at the lower frequency, so that it also has the same kV. From here, we can get kV. Okay, so we can maintain kV, we can design kV, and we can also obtain, here we want to maintain overshoot. Overshoot 9.5%. Then we get phase margin 70 degrees. Right? So this is what we designed. Please look into that again. This is another example which you can look into. You can design, then you can also use MATLAB to verify your result. In here, we want to also improve tenfold. Tenfold meaning you want to improve 10 times. But here, overshoot is 20%. Instead of 10%, this one is 20%. Okay, let's do another example. This is final exam 2014-2015. I hope you have printed these two board plot, magnitude and phase, so that we can do this example. The board plot of an aircraft roll system where when K 2.0 to 0.266. A board plot is given here with K 0.266. It's not K equal to 1 or any. It's given 0.266. For the uncompensated system, determine the phase margin when system operate at 9.5%. So first, the question asks us to find phase margin if we want the system to operate at 9.5%. And the error constant and steady state error for the uncompensated system. Okay, let's do the first one here. So we want overshoot 9.5%. From overshoot 9.5%, we can get zeta. Zeta is, if you check, zeta is 0.6. You can use the graph. And zeta 0.6, phase margin is about 59 degrees. This is number one. Okay, question one. It's not related to the plot. It just asks if you want 9.5%, what is the phase margin required? The phase margin is 59%. We can obtain using using the table here. Sorry, the two graph here, damping ratio versus overshoot, and also phase margin versus damping ratio. That is number one. Number two, we want to find error. KV, given GS, I actually forgot to add one more thing here. There will be actually a block diagram. I forgot to put the block diagram here. So this is the block diagram in the exam, given in the question. I forgot to add this. You can add, please add this in the question. K 1 over S plus 1, 10 over S plus 5, 1 over S. This is desired and roll angle, and this is actual roll angle. So the dot plot is given when K 0.266. From the block diagram, we can obtain the transfer function here, the open loop transfer function, GS. We can multiply all together, K over S, 10K over S, S plus 1, S plus 5. Right? I multiply all the 4 blocks, we get this one. And we can calculate KV. KV is limit S to 0, SGS. Is limit S to 0, S. GS is 10K over S, S plus 1, S plus 5. Okay, and we know that K is 0.266. So limit S to 0. We can solve this, cancel S. Then we can substitute S equal to 0 into the terms. So 10, 0.266 divided by 5. It's equal to 0.532. That is KV. Then we can get error. Error is 1 over KV. 1 over 532 equal to 1.88. That is the error. We can calculate. We can use calculation. This side, we can also use the given block as given magnitude to find the constant, the error constant. You can do like this. As I mentioned earlier, we can make a line, a straight line here to 0, 0 here. Okay, 0.1, 0.2, 0.3. So perhaps the same here, not much different. Okay, we can see it cross at here. 0.1, 0.2, 0.3, 0.4, 0.5. This is KV. 0.5. This is another way to find error. Then error is 1 over 0.5 equal to 2. Of course, this is not accurate. We calculated, we obtained 0.532 from the board using the board plot. KV is 0.5. Error is 1 over 0.5 equal to 2. Both are accepted. Of course, the one calculated is the accurate one. With the board plot, we need a more accurate axis, the data, in order to the value must be accurate. The graph also, but we will accept within a certain range. Right? So that is the first question regarding overshoot 9.5% and also error. Okay, next, design a lag compensator to achieve a new steady state error of 0.1. Initially, it was 1.88. This is the original steady state error. We want to find steady state error of 0.1 while maintaining overshoot at 9.5%. Want to maintain at 9.5%. Desired error equal to 0.1. Okay. That means KV, which is KV must be 10. Because 1 over KV equal to 0.1. KV equal to 10. We need to calculate a new K in order to get this KV. A new so using this formula, the formula here, the formula to calculate KV, new KV equal to 10K divided by 5. New KV is 10. So 10K over 5 equal to 10. K here is 5. So we need to use K equal to 5 in order to obtain KV 10 and error 0.1. But the graph here, the board plot here, use K 0.266. Then we need to improve, we need to modify the board plot with K equal to 5. Okay. So we want we need to examine how many dB, how many gain shifted with K equal to 5. We know that when we change K, all will be shifted up and down. In this case, because we use a higher K, a higher value of K, it will be shifted up. But how many? How many dB to be shifted? The dB we can obtain by, we have to divide K, let's say finding K1, 5 over the initial value of K, 0.266, which is, if we divide, become 18.79. That means by using K equal to 5, will be shift by 18.79. And this is not in dB. In dB, in 20 log 18.79 is equal to 25.5 dB. That means all will be shifted by 25.5 dB. So this is the problem. This problem happened because initially the dot plot was plotted with k equal to 1, k equal to 0.26. So we want to use new k equal to 5. Then we have to find how many dB, how many gain will be shifted. And this is the way to calculate how many magnitude shifted, 25.5 dB. So now I want to replot the dot plot here with k equal to 5. Here, this one, k 0.266. When we use k equal to 5, all will be shifted by 25.5 dB. So then I have to plot another one with, I add 25.5. So for example, which one is it? This one? At 0 become, hit 0 here, dB become 25, add 25. 25 is here. 25. Here at 20 become 45. 45. Here. Okay. Here 40, 45. Okay, so you just estimate, but all must be increased by 25.5. 25 meaning at about 100. Okay, so all must be 25.5 dB. Try to be accurate. This is with k equal to 5. Why we use k equal to 5? Because we want kV become 10. So the error becomes 0.1. What happened to the phase? Phase will be not affected because k, when we change k contribute to 0 degree. So no change in the phase will only affect the magnitude. All will increase, all be shifted by 25.5. Okay. So in my drawing here, perhaps this here might need to modify. All must be, the range should be the same. Right. So that is the first one. Then we want to design lag to obtain phase margin 59.2 degree to achieve 9.5% overshoot. From here, we can see that if this is correct, at 1, you may get, if you do it, you may get different point here. Let me modify a little bit here. Okay. So if we check here, when it is 0 dB, it's about 1, 2, 3, about 2.5 radian per second, W. All right, 2.5. You can see at 2.5 here, we cannot get the phase margin that we want. It's actually more than minus 180 degrees. We want phase margin of 59.2. But when we change K, it is not. It is more than 180 degrees. So we have to design a controller. We need a LED controller. So how to proceed? Remember that we normally add a correction factor of 10 degrees. In the example, we can take 10 degree. That means the desired phase margin is 59.2 plus 10 is 69.2 degrees. So 69.2 meaning here, if we plot 0 dB, 180 degrees. We want 69, that means here 100, about 110. 10, this is the phase margin that we require. Okay, when it is 0 dB. So this is what we want, 110 degree phase margin at the gain crossover frequency. This is minus 110 degrees. Right, so we have to look into the magnitude to find minus 180 degrees. One box here, 1, 2, 3, 4, 5. 45, that means 9, 99, 199, 108. So about here. This is about 110 degrees. It's here. So this is the one at about 0.3. If we can make sure this point become the phase margin, then we can get about 69.2 phase margin degrees. According to what we want here, 69.2. It happen at frequency 0.3 radian per second. So we need to make sure at 0.3 here, the magnitude cross 0 dB. If we can make sure it cross 0 dB, then it will be, we can obtain the phase margin that we require. So now look into 0.3. Here, 0.3, you see the magnitude here. The magnitude is about 28 dB. Yeah, again, if you do it yourself, you may get maybe get 32, may get 24, 30 something. The one here I just estimate as at 28. So what to do next is now we need to draw the gate, the lag compensator at the high frequency gain. How to do? We need to put minus 28 here, minus 28, so that at this point, added with the lag compensator, that point becomes 0. So that means we need a compensator with the gain here is minus 28. So that 28 plus minus 28, then this point becomes 0. And if at 0.3 radian per second we get magnitude 0, then we can make sure we obtain the phase margin that we require. Okay, the way to design 0.3 at 28, we move into, we have to make minus 28 dB for 1 decade. 0.3, then we see 0.03. Here, 1 decade, 0.03. So the line here is up to 0.03. Okay, next, what to do? We need to draw a line which is 20 dB per decade negative until 0 dB. This is a line of $20 per decade. 1 decade, 20 dB. See? 1 decade, it changed from 40 to 60. So the line here must be in the same slope as this line. If we make another line, same line here. So we can make a line similar to this slope. I just estimate here 0.03, 1 decade, 0.003, it will be here. This is a line of minus 20 dB per decade. Okay, you have to take 1 decade, then make it 20 dB. But we need to continue this line until 0 dB. Then, before that, it will be 0. Why we need 0? Because we want to maintain the slope at the beginning, at the low frequency region, so that we can get KV that we want. So this is the lag compensator that we need in order to achieve overshoot 9.5%, KV equal to 10. Any question before I proceed? Any question? You can only understand if you do together, and you have to do on your graph paper. You may get a slightly different value. Then the most we need to get two important points here and here. This one we already know 0.03 here, and here is from the one that I did here is 0.002 omega. Right? So so the one that we obtain is like this. It is like this, going down, and then maintain here. At this point is 0.03. Here is 0.002. I mentioned yesterday, it is actually a combination of two components. Is this one plus the other one like this. So finally, we can write the transfer function G let is actually the one at the for the numerator is 1 over S over 0.03 divided by 1 over S, 1 plus S over 0.002. So that is the transfer function, and we can rewrite 1 over 0.03 S plus 0.03 over 1 plus 0.002 S plus 0.002. Right, then we can proceed. We can also rewrite again. We can proceed. We can rewrite again the equation, the transfer function, 1 over 0.03 divided by 1 over 0.002. Is 0.0067. 0.067 S plus 0.03 over S plus 0.002. So this is the transfer function of the LED compensator. We can show the complete transfer function in which we multiply G with G LED. Right? G was 10, 10K, K 5, S plus 1, S plus 5. We can multiply with this, with G LED, become 0.067, S plus 0.03, divide by S plus 0.002. Okay, then you can solve this, can get the final one. So that is how we design a LED compensator. The question asks us to show the complete transfer function of the compensated system. So this is the one. This is the compensated system.
Doctor, I have a question.
Yeah.
The complete transfer function, we leave it like that or we must solve?
No need. You can multiply all this, just that one.
Oh, just the number.
Yeah.
Okay.
If you multiply this one, it become 3.35 S plus 0.03 and this, just this. So this is the complete transfer function. If you just to confirm, remember the question also asks, verify the desired steady state error is obtained. We want steady state error of 0.1. With this, we can again calculate KV. KV limit S to 0 SGS. We can solve this, and you can see that KV is about 10. I've tried, is KV almost 10. So error is 0.1. Right, so that is question 2014-15. I would like you to do another question here as a homework. They are similar. First, it is drawn with K6.4. Then they ask what is the phase margin for 25% overshoot, find error, and find constant error constant and also steady state error when K6.4. You can calculate or you can also obtain from the graph here. Then design a lag compensator to reduce the steady state error by 20. In the first question, they give 0.1, but here is by a factor of 20 from the original one. So it is important to find the original one. Then we divide by 20 while maintaining at 25% overshoot. Okay, please do it. We can discuss again in the next class, but please do this first, okay, so that you know the process. You can ask if you have problem. You can ask in the group or you can ask personal, but you need to try. Okay. Any question before we end lecture today?
Doctor, can I ask about the assignment?
Uh-huh.
At the task 3, is